Hello, everyone. In this video, we will cover natural logarithm. In the previous video, we covered exponential function and exponents as a review for the prerequisite materials for advanced engineering analysis. So before we start with natural logarithm, let's cover what natural exponential function is. Natural exponential function is defined as e to the power x, and here the number e is a constant, which is approximately 2.718 and some other digits. Now let's go over natural logarithm function, and then we will see how natural exponential function and natural logarithm functions are related. Natural logarithmic function is defined as ln x. X is the argument. This ln is for the natural logarithm. And natural logarithm and natural exponential function are inverse functions, and we will get to this point very soon. So let's first define natural logarithm. Ln of x is equal to y. So if natural logarithm of x is equal to y, then argument of the natural logarithm, which is x, should be equal to e to the power y, or basically e to the power y is equal to x. So this is the definition of the natural logarithm. Note that x, the argument of natural logarithm, should be a positive real number. So now let's solve a couple of examples. An important case is natural logarithm of 1. Okay, so let's solve what natural logarithm of 1 is equal to. First, let's consider that natural logarithm of 1 is equal to y. We don't know the value of y now, but this is what we will be finding out. Using the definition of the natural logarithm here, we can show that argument of the natural logarithm, which is 1, equals to e to the power y. And we have learned in the previous video that from the properties of exponents, any positive real number to the power 0 equals to 1. This includes the number e. So the number e to the power 0 is also equal to 1. So we can write 1 as e to the power 0, meaning that left side of the equation, e to the power 0, has to be equal to the right side of the equation, which is e to the power y, which means that exponents, since bases would be the same, exponents has to be the same, so y should be equal to 0. So ln 1 should be equal to 0, because if y is equal to 0, then ln 1 equals to y, which is equal to 0. So this is important case that we will also utilize later on in different examples. As another example, another important case is natural logarithm of the number e. Now, using, again, let's consider that ln of e is equal to y. Using the natural logarithm definition, then argument e is equal to e to the power y, using this here equation. On the left side, e is e to the power 1. And on the right side, we have e to the power y. Left side has to be equal to the right side. So y should be equal to 1, because bases are the same, right? So exponents also have to be the same. You know, exponent on the left side is 1. So the exponent on the right side, which is y, should also be equal to 1. Then ln of e is equal to 1. So natural logarithm of e, number e, is equal to 1. This is an important case as well that we will use later on. So now let's go over some of the properties of logarithms. Consider that x, y, z symbols that I will use in this discussion are positive real numbers. So they represent positive real numbers. As the first property, ln of x times y, or multiplication of x and y, is equal to ln of x plus ln of y. Okay. As an example, consider natural logarithm of 6. We can write 6 as multiplication of 3 times 2, or we can consider it as 6 times 1, whichever you prefer. So let's consider ln is equal to ln 3 times 2. Then we can use this property and we can write that ln 6 is equal to ln 3 plus ln 2. If we have picked 6 times 1 as the argument, 6, then we would write is equal to ln 6 plus ln 1, and the result would be the same. All right. As the second property, ln natural logarithm of x over y can be written as ln of x minus ln of y. Since it's y is in the denominator, note the sign here, it is negative. It is not positive as in property 1. As an example, consider natural logarithm of 6 over 3. We can write this as ln 6 minus ln 3. As the third property, consider ln x to the power z. Here z is the exponent of the argument x, or x to the power z is the argument, but this is an exponential function. Argument is an exponential function with the exponent z. So these properties say that we can write it as z times ln x. Basically, the exponent becomes a multiplier of the ln of the base of the exponential function. So ln x to the power z can be written as z becoming multiplier of ln x. As an example, consider natural logarithm of square root of 2x plus 1. We can write the square root of 2x plus 1 as 2x plus 1 to the power 1/2. Remember, the power of 1/2 means square root. Then this is the exponent of the exponential function, which is the argument of natural logarithm. So we can move the exponent as the multiplier of the natural logarithm function with the argument, which was the base of the exponential function, 2x plus 1. Another example is, now consider natural logarithm of e to the power negative 1. Here we can show it in two different ways. Let me show you. I'll just verbally describe. Same property, very straightforward. Just take this multiplier, this exponent as the multiplier. So you have negative 1 times ln e. We have already shown in the previous examples that ln of number e is equal to 1. So negative 1 multiplied by 1 is negative 1. So the answer here is negative 1. But let's solve it using a little bit longer way, another alternative way. So ln e to the negative 1, consider that it's equal to y. Using the definition of the natural logarithm, we can write argument e to the negative 1 is equal to e to the power y. The right side and left sides of this equality has to hold, right? Has to be equal, this equation. Bases are the same, e. So exponents has to be the same. So y should be equal to negative 1. If y is equal to negative 1, then ln e to the negative 1 is equal to y is equal to negative 1. So this is the answer that we obtained from the definition of natural logarithm. But you could also obtain exactly the same result using property 3. Now let's consider, I mentioned that natural logarithm and natural exponential functions are inverse functions. So let's go over what I mean by that. So they are inverse functions, meaning that ln of the e to the power x exponential function is equal to x, and e to the power ln x is equal to x. So if they are inverse functions, these two expressions should hold. Basically, natural logarithm of e to the power x will give you x, and e to the power of ln x will give you x. So let's show that these equalities or these expressions hold, are valid expressions, so that these two functions are inverse functions. Now let's go first with the first term, ln e to the power x is equal to x. Let's focus on the left-hand side, ln e to the power x, using the properties that we discussed. E to the power x, this x is exponent, so we can move it as the multiplier here of the ln, and now the argument is just the base of the initial exponential function. We have already shown that natural logarithm of e is equal to 1, so x times 1 is equal to x, which basically shows that this equation holds. Now let's show that the second equation also holds. Now let's show that e to the power ln x is equal to x. Consider e to the power ln x is equal to y. So we are just focusing on the left side now, and we assume that left side of this equation is equal to y. Basically, we just need to show that y is equal to x. If we can show that, then we prove this equality. Now, what you need to do is now take both sides, the natural logarithm of both sides. So natural logarithm of e to the ln x is equal to natural logarithm of y. We know that this exponent ln x here, the one that I'm circling, we can basically, using the properties that we discussed, we can move it as the multiplier of the ln function. So we can write it as ln x times ln e, this left side, and the right side remains the same, ln y. We have already shown that ln of e is equal to 1. So we have 1 times ln x, which is ln x. So ln x is equal to ln y. So the arguments of the natural logarithms on the left and right sides has to be identical, which means that x is equal to y. If y equals to x, then we can write that, or if x equals to y, we can write that e to the ln x equals to y equals to x, which basically proves that these two functions, natural logarithm and natural exponential functions, are inverse functions. And these are important properties that we can use also in algebraic simplifications that we will conduct. Now, as an example, let's solve this equation for x. So e to the power x plus 1 equals to 1, then calculate x. Here, using the definition, or instead of using the definition, we can take the natural logarithm of both sides, ln e to the x plus 1 equals to ln 1. We know that ln 1 is equal to 0. This is something that we have shown as an initial example. So we have x plus ln x plus 1 equals to 0. Remember, as the property, we discussed that this exponent can be moved as a multiplier, which means that x plus 1 times ln e should be equal to 0, because right-hand side is equal to 0. And we have also shown that ln of e is equal to 1, so this is 1, meaning that x plus 1 is equal to 0. Then it is x equals to negative 1. All right. As the next example, now let's consider natural logarithm of 2x minus 2 equals to 0. If that is the case, then what is the value of x? For this, now let's use the definition of natural logarithm. Ln 2x minus 2 equals to 0, then the argument 2x minus 2 should be equal to e to the power 0. We know that e to the power 0 is equal to 1. This is something that we learned in the previous video when we discussed the properties of exponents. Then 2x minus 2 equals to 1, which is 2x is equal to 3. Then x is equal to 3 over 2. All right. Now, let's go over an example for algebraic simplifications. Consider that we have an equation of this form. It has two variables, x and y. And let's say we want to simplify this equation to obtain an expression for x in terms of y as a function of y. So here, let's start simplifying this equation, starting from the first term. We can write this equation as 5y, 5 times y, times natural logarithm of, instead of 1 over e to the power 5x, we can move the denominator to the numerator as e to the negative 5x, okay, plus we keep the rest same, 3x equals to 2 plus 3 times x times y. Now, we have a negative 5x as the exponent, which we can make it a multiplier. So first term, just focus on this first term. We have 5 times y. Now the exponent becomes the multiplier because of the properties that we just covered. So 5y times negative 5x times ln e. And ln e, we know that is equal to 1. So we have 5y times negative 5x plus 3x equals to 2 plus 3xy. All right? So the first term, 5y times negative 5x is negative 25xy. The rest is the same for now. 3x equals to plus 3x equals to 2 plus 3 times xy. Now, as you can see, we have negative 25xy on the left and positive 3xy on the right. So we can combine these two terms with the same variables. So we moved, let's say, the positive 3xy to the left side of the equation, which becomes negative 3xy. When we sum it up with negative 25xy, we end up with negative 28xy plus 3x is our second term, is equal to 2. Now we have x as the common term on the first on the terms on the left side of this equation. So we can put them in the common term parentheses. So x times 3 minus 28y is equal to 2. And we can further manipulate this expression as x equals to 2 divided by 3 minus 28y. So basically, we obtained an expression x as a function of y, as you can see in this boxed area. All right, so that's all for this video. Thank you, and I'll see you in the next video.